All right, which is something you guys, single phase power is something you guys should have seen. So first of all, what do I mean when I talk about phases? What's a phase? Who knows?
The phase shift in like a sine wave when you delay it or advance it. But...
Well, yeah. So phase shift talks about how much I delay or advance from zero, and how much I delay or advance a cosine from zero. When I talk about it, in the context of power, we're talking about usually that concept. We're talking about how the voltage sources get shifted from zero. So some of you guys have heard, and hopefully a lot of you saw in 2112, three-phase. We're going to talk about three-phase a little bit next week. Because when we talk about machines, we hook them up to the grid, and the grid is three-phase. So we got to deal with three-phase. This is what you have in a house, all right? Whether you realize it or not. So first of all, I used RMS here, all right? So what's that mean again? So if I have a sine wave, and I said that voltage is 120 volts RMS. What's the peak value of that? So first of all, it looks like a sine wave, right? And in fact, actually, if I say it's 120 angle 0, it doesn't look like a sine wave. What's it actually look like? Cosine wave, right? So angle 0 means I got a cosine. What's the peak value, or in other words, what's the amplitude of that sine wave? It's not 120, is it? Around 170. So how'd you get that? 120 times what? Square root of 2. All right. The peak value is 120 times the square root of 2. Now, notice this is my house. My house, I have something called split phase. All right. That's just an industry term. But if I look at those two right there, so you may have heard in your house, you got 120 and 240, right? So what's hooked up to 240? I guess I gave the example. I got an air conditioner that's hooked up to 240 volts. What else is hooked up to 240 volts in a house? An oven might be, a dryer might be, right? Something that requires a lot of power, right? What you actually have is two voltages that are 180 degrees out of phase with each other. So it looks something like this. And I use the terms here. There's a hot, which is the plus, and the neutral, which is the minus. Okay, I'm going to use those terms a little bit as I go through here. But what I'm trying to show here is you got a couple of single phase circuits. Those are the 120 circuits where my example here, I've got light bulbs hooked up to those. And then I have 240, which is basically the two of them. Now, why do I know that so phasors like this, 120 and 120, how do I know they're going to add to 240? If I tried to draw those sine waves, something showed up wrong when I made that slide there, but what's true about those two? If I drew those two sine waves, so the one that's 120 angle 0 and the one that's 120 angle 180, what would they look like? So the 120 angle 0 would look like this, right? What would the 120 angle 180 look like?
Do the negative of that.
Yeah, the negative of that. So if I end up subtracting those, what do I get? If I add those, I get 0, right? If I subtract those two things, what's it become?
You get 240.
I get 240, right? So if you were to go to your house and you were to measure, basically with an oscilloscope across two outlets, you might find 240 volts. Okay. All right. So anyway, we're going to deal with that. This is what we call split phase. All right. This is what you have in a house. In a building, you can have three phase. I'm going to talk about that more. But that's what the concept of a phase sort of means. Okay. All right. So should we make sure we cover that, because that's an important thing to just have baseline understanding of. All right, so the other thing we talked about the other day, we talked about this idea of power, and I've got written what it is here. It's the rate at which we use energy. So what was W again? Energy. What is W? Work. Right, work and energy are equal to each other, same thing. It's the rate at which we're using energy. And something I didn't really mention the other day, but if I show a load like this, right, where I'm using the passive sign convention. What the heck was that thing again? Passive sign convention.
Always the current flows into the positive.
Yeah, when the current flows into the plus node, the power is positive.
Yeah. Okay.
And V would equal to I times R. If current was coming out of the plus sign, V would equal negative IR, right? All that stuff. But basically, we're going to use this terminology whenever that's true. V of T and I of T are written that way. P of T, All right, P of t, just as I have it written there, we call this instantaneous power, and we are not going to deal with that much. It's telling me how much power I have at any given point in time. All right, V of t times I of t is instantaneous power. Whenever that's positive, the load's absorbing energy. Whenever it's negative, it's sourcing energy. Right, energy's flowing out of it. Okay. All right. You're not going to deal with that concept a whole lot. We deal instead not with P of t, the power is a function of time, but you guys should probably know we deal with capital P and capital Q. What is capital P? This is a little p of t. I'm going to deal with capital P. Real power. How does P of t and capital P, how do they relate to each other? You better remember.
Little p is equal to big P plus.
Little p is V times I, just V times I, just as you learned it with DC circuits or in physics. P is the average value of that. So in other words, if I take the average over a period of P of t, it's the average value of it. All right. Now, without getting too, I don't want to get too lost in the weeds on this, but I want to remember you learned in physics, power is V times I, volts times amps. Okay. That's what it equals at some given point in time, but that tends to look kind of ugly. Okay. If I look at P of t, right, which is V of t times I of t. Okay. Just to be clear, that's V times I. It looks like that, and it's ugly. Okay. When I say it's ugly, if I look at this guy, I've got this cosine 2 omega t, this sine 2 omega t. There's all this junk that's here. All right, but what we see is when we so what I did here is if I take V times I, where basically in the way that I did this, I took V of t equals V peak times cosine omega t plus phi V. Okay. And I of t equal to I peak times cosine omega t plus phi I. If I take those two things and multiply them out, I get that ugly thing. Don't bother writing it down. All right. What does matter is those two things. All right. What this thing says is, first of all, there's three terms in the resulting multiplication. I'm not gonna ask you to derive stuff here. I want to apply it, right? P of t equals that thing. I got a constant term plus some other term that has a cosine 2 omega t plus some other term that has a sine 2 omega t. Okay. This is the average value. Okay. And we call that real power or active power, P. And then we have this other term that we just define, which is this thing right here, this coefficient that we call reactive power. We define it that way. All right. Now, if I just try to understand, well, what's going to happen, right? So if I have a couple of different types of loads, what's the P of t going to look like? Okay. So I'm going to start out with a resistor. All right. So I have a resistor. So here's what I'm going to do. I have something that's 120 angle 0, and then I have a resistor. So let's say I had basically this circuit right here. Okay. Where this guy is 120 with an angle of 0 degrees. Okay. And this is 144 ohms. Okay. I want to figure out here, what is the angle of the impedance in this circuit? What's the angle of the impedance? So my impedance is an R. So what's its angle? 0. Okay, that's good. So what does that mean again about the current? If I think about the voltage as a sine wave and the current as a sine wave, what's that mean about the current and voltage? They're in phase. They look like each other. They just have different amplitudes. Okay. So if I want to figure out what I is, what is I? Nothing complicated. V over Z, yeah, so V over R, right? So it's going to be, in this case, if I do the math, it works out to 0.833 amps. And what's the angle going to be? 0, right? They all got the same angle. So if I draw that in my phasor diagram, where do I draw all three of those phasors? On the real axis, right? So there's this guy, this would be voltage, and then impedance, I guess, would be a little bit bigger. And then the current would be this wee bitty thing relative to those two, right? Because he's a heck of a lot smaller, right? Now, if I went through what P of T looks like, and I don't want to do that because it's going to be nasty, right? Basically, it would be 100 plus 100 cosine 2 omega t, like that. All right, as if I plugged everything into those formulas, that's what I would end up with. What's that going to look like?
Sine wave with a DC offset.
It's a sine wave with a DC offset. So if I looked at this P of T, what's its minimum value and what's its maximum value?
100, 100. Negative. 100, 200. 0, 200.
0 and 200, right? So whenever this guy goes between negative 100 and 100, so you add that to 100 and it's going to go between 0 and 200. Okay, so I'm going to get some result that's between 0 and 200. Never goes below 0. So what's that mean? If the P of T is always positive, what's that tell me about the load? There, it's always absorbing energy, and that's what a resistor does. It's basically just making heat. Okay, it's always absorbing energy. It's got no energy storage capabilities. All right. What's the average of this thing? 100. Okay. Because how do you know that? Well, what's the average value of a cosine? Any cosine. Yeah, the middle value. So the average value of cosine of t is 0, right? So the average value of this thing is 100. Okay. So if I try to visualize this, right? Here's V of t, right? That's 120 with an angle of 0. This is the current, that's 0.833 with an angle of 0. And what I did here was P of T. Now, what do you notice about the frequency of P of T relative to the frequency of the voltage and the current? It's twice the frequency, right? How do you know how does somebody other than Musa know that it's twice the frequency? What can you tell about it? Why do you see that that's twice the frequency?
Half the width.
What do you mean half the wave?
Like the wave.
Yeah, basically this guy varies twice in one period of that. Right. So if in one period this guy had 2 periods, he's got twice the frequency. He's twice as fast. Okay. So what I did was I took the average over that period. And the average of that thing is basically that line right there. That's 100. This is a 100-watt light bulb. Okay. That's basically what this is. Again, the important thing that what I want you to understand with this, because one of the questions everybody asks is, why do we do 3-phase? Well, we'll see that when we do 3-phase, P of T doesn't have this fluctuation. Right? P of T is actually just flat. All right. And one of the good things about 3-phase is they don't have that fluctuation. That's good for motors and all sorts of stuff like that. Motors don't like power to fluctuate. You ever seen a single-phase motor? Have you ever seen a 3-phase motor? I probably haven't seen either of those, but in your house, you have single-phase motors. Okay. Any idea how big is like the fan in your air conditioning unit? Any idea how powerful that fan is in your air conditioning unit? You've looked at your air conditioner. Yeah, it's probably about 1/6 or 1/5 of a horsepower. All right. 1/5 of a horsepower. I don't mind grabbing the shaft of that motor. I don't think it's going to hurt me too bad. Okay. 100 horsepower, I don't want to grab the shaft of that motor. My arm will rip off. Okay. That's a tiny motor. You know, basically above 5 horsepower or so, which is like nothing. I showed you a picture the other day of a motor that was 100 horsepower, right? If I have a motor that's 1/5 or 1/6 of a horsepower, single phase is fine, right? It's a piece of crap that's made, you know, in China at the lowest possible cost, right? That's not the case if I have a big motor, right? And so the reason why I'm okay with single phase in a crappy motor is because this stuff is not good for performance. But I can deal with that if it's a crappy motor, because it doesn't have to perform well. It just has to move air through your house. All right. But if I am making stuff and I need a high performing motor, I don't want that. Okay. always positive here. So what do you think is going to happen in my second case when I have a pure inductor? What's going to happen in that case? Well, it's a good thought. Yeah, is it what it's there's going to be some negative, right? So it's not going to be always negative. What would be always negative is if I have a source. A source is always going to be negative because it's always giving energy. All right. In this case, the pure inductor is going to be a little bit positive and a little bit negative. So what's it mean? When it's positive, it's absorbing energy. When it's negative, what's it doing? Giving energy. How can it do that? How can it absorb and how can it give back? What's true about an inductor that isn't true about a resistor? It's a what? It has memory, right? It has energy storage, right? It has energy storage. So it can source as much as it took in, right? So it's going to take some in and it's going to give it back. It's going to take some in, it's going to give it back. Okay. So if I have a pure inductor, let's go through that case real quick. All right. So I said omega L is 144 ohms. What is omega L here? It's almost the impedance, right? It's not quite the impedance. What is omega L? It's the what of the impedance? Magnitude of the impedance. All right. Now, the impedance here is J omega L. All right. So somebody other than Joey and Musa, what's that mean? J omega L. What's this means? This guy has got 144 ohms. With what angle? Wait, other than Musa? 90. Okay. All right. 90 degrees. If you can't remember why that is, the way I always think about that is if I said I had basically, 0 plus J 144. If I were to draw that in the complex plane, that guy would be up here, right? On the imaginary axis. Okay. Now, I is V divided by Z. Okay. All right, so let's do some good old-fashioned complex number stuff. So I've got two phasors dividing each other like that, right? So how do I get the magnitude and the angle when I divide two phasors like that?
Divide the magnitude, subtract the angles.
Divide the magnitude, subtract the angles. Yeah, so I've got 120 divided by 144. And the angle is going to be 0 degrees minus 90 degrees. Right? So this guy's going to work out to be 0.833. 0.833 angle negative 90 degrees. All right. So the voltage, so let's help me with my phasor diagram here. Where do I draw the voltage phasor and where do I draw the current phasor?
Voltage on the real.
Yeah, voltage is on the real axis. He's over here, almost as big as Z. And I still got this wee little tiny thing for the current. Like that. Right? Now, what did we said the other day? The voltage for an inductor, the voltage leads the current. All right. And the way that I always remember that is the voltage has an angle that is more positive than the current. Right? More positive meaning it's farther along in the rotational cycle. And I don't bother to remember that. What I really do is I remember V equals I times Z. So that means that the angle of the voltage equals always the angle of the current plus the angle of the impedance. Right? And that's how I can always work that out. Now, if I go through and do this whole thing, and I work this guy out, this guy's going to work out to be 100 times sine of 2 omega t. That's what my P of t is going to work out to be. Okay. And again, don't get too lost in this P of t thing. What do I see about this? If I plugged in all the numbers, I'd get this. What's the average value of this P of t? 0. right? Because the average power transferred to load is 0. Average power represents real work that's happening, right? So if I look at case 1 here, where I had pure resistor, all I have is work, right? What I'm doing is I'm transferring energy from a source. And what am I doing? What is this thing? This resistor. What is it physically? It's a heater, right? That's what this thing is. It's a heater, right? If I stood near it and it was cold outside, I'd feel warm, right? That's what this thing is, basically a heater, all right? You go into a heat pump. Heat pumps sometimes have backup power called heat strips. They're just basically big resistors and there's air blowing over them, okay? So it's a heater. All it's doing is making heat. Whereas in this case, what's happening? Well, sometimes P of T is positive, sometimes it's negative. So if I look at this case, right? So there's the voltage and the current. They're 90 degrees shifted from each other. Right. So notice I can see, all right, when the voltage is at its peak, I see the peak of the current is behind it by 90 degrees. Why do I say it's behind it? Why do I say the current's behind the voltage? Why is this behind this? It's a lag in time. All right, it's a lag in time. And that manifests here by saying that this guy, I have to go to get from voltage to current, I have to go negative 90 degrees. I have to go, what is that? Clockwise. Clockwise is a negative rotation. Okay. All right. Important thing here is if I look at this, this guy is positive half the time and negative half the time. So whenever this guy is positive, he's absorbing energy, and whenever he's negative, he's giving it back. He's an energy storage device. He's not doing any real work, right? He's storing and he's giving it up, storing, giving it up, storing, giving it up, right? Now what happens in my case 3, right? In my case 3, where I have an impedance, in this case, it's an R plus J omega L. The magnitude's 144 degrees and the angle is 45 degrees. All right. So let's think about the phasor diagram here. My voltage is still here. There's my voltage. Forget that square root of 2. I think I was switching between peaks and RMS. Where do I draw the impedance here? I said it's 144 magnitude with an angle of 45 degrees. So where's that guy? Yeah, so he's going to be up here. Here's Z. And where would I be? Well, I is V divided by Z, right? So when we're doing the math here, again, I don't like memorizing stuff like this lags, this leads. I don't like to memorize anything. I know that I equals V times Z. That's the only thing I know. All right, I only know 3 things. I equals V times Z, KCL, and KVL. That's it. Anything else I'll look up. Okay. How do I figure out what the angle of the current is? Well, I just do V divided by Z. So how do I get the magnitude and how do I get the angle from that? By the magnitudes, right? So not surprisingly, I didn't want to do the math over and over again. So 120 divided by 144, right? And my angle is 0 minus 45 degrees. All right. So where's the current vector going to be?
At negative 45 degrees?
Yeah, negative 45. And he's going to be small again. He's going to be 0.833. So if I go through this whole P of T thing, what I'm going to end up with is that this is 70.7 plus 70.7 times cosine 2 omega T plus 70.7 sine 2 omega T. If I look at this guy, he does have an average. What's the average value of this thing? 70.7, right? Now, if I put everything together, here's what I'm going to see. It's still going 200 watts peak to peak, all right? But when I look at this, some of the time he's negatives. Here's the 0 line right there. Let me do this here, probably. Here's the 0 line, right? So here he's negative. And then the rest of the time, He's positive, right? This what now? So what's going on here? Well, he's got some storage and some real work, right? And the average is the real work that he's doing. So he's not doing as much work as this resistor was, right? This guy was doing a lot of work, which means he was making a lot of heat. This guy's making a little bit less heat, right? But he's also got some storage. Okay. Important thing is basically this: if I have in all three of these cases, right, all I have here is work, nothing but work, right? And specifically, that means I'm making heat. Right. In this case, I got nothing but storage. Right. In this case, I've got work plus storage. And one of the points I made the other day is, what are most loads that we have? Well, most loads that we have are usually case 3, where I have some combination of work and storage. Right. Most common thing is like a motor. All right. The biggest amount of load in the world is motors. All right. And the other big chunk of it's lights and computers. All right. Most of these things, a lot of these things are motors. All right. And they're just combinations of resistors and inductors, or resistors and capacitors. All right. And so just we need to understand what those differences are. Now, what you should remember, hopefully, is this guy is all real power. This is all what kind of power? Reactive power. This is P only. This is Q only. And this is P plus. I mean, I don't want to do it that way. P and Q together. Right? It's the two of those. Okay. All right. You're not going to be doing a lot of stuff. You should know how to manipulate phasors. All right. I don't want to spend all, you're not going to do P of T. All right. I just wanted to go over that concept. I think it's important. Why do we use RMS values? So one thing I guess I did want to talk about, because we use RMS kind of exclusively, right? If I had this circuit, right, a DC circuit, and I asked you what's the current, you would say, well, if I know what R is and I know what V is, V divided by R is I, right? So when I do this, I get 0.833 amps. Similarly, if I'm looking at a DC and an AC circuit, where I have something that's 120 times square root of 2, like that. Same exact light bulb, and you can do that. You can put a light bulb into a DC circuit, you can put it into an AC circuit. It'll be fine with it. Okay. If I do this, the important thing is all of the AC circuit values when I use RMS are the same as what they are in DC circuits. All right. And so everybody likes that. Basically, sometimes we call this RMS, sometimes we call it an effective DC value. You see people term it that, right? The reason we do it is it basically just makes everything look the same as if it was a DC circuit. And that's the reason why we use it. All right. It makes our formulas get a bunch of extra 2's disappear and stuff like that. So that's the main reason why we do it. Okay. All right. Key thing that we just figured out, right, is we make 2 definitions, right? One of the definitions is that in these single phase circuits, what I have is this real power and this reactive power, those 2 things. Reactive power is basically, this relates to the energy storage in the circuit. This relates to the energy storage. And this real power relates to the real work. Okay. So the formula for those 2 things is basically right there, right? And in the notes that I posted, I go through some derivations and stuff like that. But one of the things that I have, which I'm about to kind of go through here, is I have a whole summary of all the relationships that kind of exist between those things. Okay. So there's a whole set of relationships between P and Q and some other things we're about to talk about. So it's summarized here in this. It's also summarized in the additional notes that I posted. Okay, so you guys can go in and you'll probably want to look at that when you're going through your homework. Okay, but I want to. These are the 2 things that we remember. Now the thing is, if I look at real power and reactive power like that, there's a couple of things that I want to note about these two things. So they look pretty similar to, you know, for DC circuits where I said it's V times I, except I got these cosine and sine things. Okay. Now, one thing I want to note here, so I say cosine of phi V minus phi I. So just to be clear, the V vector, so I'm talking about a load that has this setup. Here's V, here's I, like that. V is VRMS with an angle of phi V. And I is IRMS with an angle of phi I. Okay. So phi V minus phi I has a meaning, right? Where does that meaning come from?
Also phi z.
Well, it's, yeah, you jumped the gun on me, yeah. Where do I, so phi V minus phi I has a meaning, and its meaning is what Musa just said, it's the impedance angle. How can I figure out that phi V minus phi I is the impedance angle? Well, again, I said I only know three things. I don't, my brain is small. That's one of the three. Okay. V equals I times Z. So that's really two equations, isn't it? One's magnitude, one's angle. What's true about all the angles here for those three vectors? What's true about the angles of those three vectors?
Phi v equals phi.
Phi V equals phi I plus phi Z, right? Because angles add when I multiply vectors. So that tells me that phi Z is what? Phi V minus phi I, right? So I can say this guy is VRMS, IRMS times the cosine of phi Z, like that. Do it this way. V equals IR, right? This is VRMS, IRMS, sine of phi Z. Okay, if I look at that, P and Q, I've got the same magnitude times the cosine and the same magnitude times the sine. So that means that those two things form a what? They're the real and imaginary parts of a vector, of a complex number. All right. Which one is the imaginary part and which one is the real part? Somebody, you know. All right, you're silenced for the rest of the class, Missy. Yeah, it's P, this guy is the real part. This guy is the imaginary part. So that forms, sometimes people call this the power triangle, right? Oops, that was a really bad line. The real part here is P. The imaginary part here is Q. Okay. And this guy is phi sub Z. Okay. This guy here is called phi. So the angle of that vector is the same as the impedance angle. Okay. And sometimes this is called the power triangle. Okay. Now, we also give a name to this thing here, cosine of phi Z. We don't give a name to sine of phi Z, but we do give a name to cosine of phi Z. What is cosine of phi Z? Power factor. And what do we like power factor to be? Anybody remember? 1. So we want the angle to be 0, right? Which means that makes the power factor 1. So what's true about the impedance? If the power factor is 1, the angle of the impedance is 0, so the impedance is a what? A resistor, right? What's that mean in terms of power? That means that the only thing that load is doing is work. That's usually a good thing. We just want our loads doing work. All right. Yeah. Rachel.
If they ask like power factor whether it's leading or lagging, are we determining that based on the voltage or the
we're determining that based on whatever we're given. So usually it's based on the impedance. It's based on whether it's an inductive load or whether it's a capacitive load. Okay, so we're actually gonna do an example to do on that one here in a little bit. Okay. Good question. All right. So basically what that says is we put those together, the vector we call it S. All right. I don't know why S, but S is what we call it. All right. S equals P plus JQ. So I can put the P and Q together. There's a whole crap load of formulas here. All right. I don't want to deal with all those formulas. That's why I put that summary sheet together. Okay. If I look at this, right, the magnitude of this thing is termed the apparent power. Okay. And the magnitude of so based on what I have here, what's the magnitude of this vector, the magnitude of S? What is that? In terms of the variables I have here, what's the magnitude?
Root P squared plus J squared.
Well, it would be P squared plus Q squared, square root, for sure. And what's that relate? How does that relate to the voltage and the current? So what's the step between here and here? Yeah, VRMS times IRMS. Yeah. Now I have this summarized again in the notes, but we give these things different units. Okay. I want to skip ahead for a minute here. I'll come back. All right. Basically, what I have is apparent power, real or active power, all right, P, and reactive power, Q. All their units are different. Now, all their units are volts times amps. Okay. The only one that gets watts is the real power. When I talk about Q, we call it volts, amps, reactive, or VARs. When I talk about apparent power, I talk about volt amps. Okay. So, I know you guys have seen this before, but haven't thought about it, probably most of you for at least a year, some of you for longer. Okay. But it's all summarized here, and we're going to get up to speed on it fairly quick. Okay. This S thing is the complex power. It's putting it into a vector. Okay. Now, one thing I notice about this when I look at those things together, right, is when I look at that S, that P plus JQ, whatever, and I put it together, I have the two components of it, right? This thing right here, right? If I look at it carefully, the way I would get this result would also be if the voltage vector was V RMS with an angle of phi V, and the current vector was I RMS with an angle of phi I, this thing would end up being, if I looked at this carefully, it would be V RMS angle voltage times I RMS times the negative angle of the current, right? This basically looks like so if you did this multiplication out and converted it into Cartesian form, you would get this result right here. Okay. IRMS with a negative angle of I. What's it mean when I take the negative angle? Conjugate. You're turned off, Liz.
Yeah.
Okay. So it's V times I conjugate. All right. So we need to remember those. So in summary, basically, our relationships are those. Okay. I don't want to get through all that sort of stuff, but basically, those are the primary things, and I've got it all kind of summarized here for what the standard forms are for all this sort of stuff. Okay. One thing I do want to talk about real quick, it gets to the point that Rachel was just kind of asking about. All right, if I have an inductive load, if I had a pure inductor, I don't want to show that just yet. If I had a pure inductor, what's the angle of the impedance for an inductor?
90 degrees.
90 degrees. Yeah. So if I have what I call an inductive load, that's going to be some R plus some inductance. So what's its angle? What's the angle of the impedance always going to be? If I have R plus J omega L, that's what I'm going to call an inductive load. What's the angle of its impedance always going to be? It's always going to be positive. All right, so it's never going to go below 0, but it's also never going to go above a particular number either. Never going to go above 90. All right. Similarly, for a capacitive load, it's always going to be negative, and it's never going to go below negative 90. All right. So when I say an inductive load, what I mean is it's R plus J omega L. And if it's capacitive, it's R plus 1 over J omega C, like that. All right. That's what we need. All right. So what that means is our Q in one case is positive, and in one case is negative. Okay. Again, we're going to look at an example here in a second. We've done too much talking about theory stuff. I know I've tapped your brain out on theory. All right. So the summary of all of it is here basically. All right. And we're going to use that. All right. But I want to do a problem because we all think better that way, probably. Okay. So this is one that's similar to what you have in the homework here, where what I've got is a voltage source. So let's just make it clear that I got a voltage source, and I don't know what it is. All right, we're going to solve for what it must be. What I've been told is what the voltage is across the load. I got two loads in parallel. This is common in power. In power, I often don't show what the impedance of the load is. I just say it's a load, right? It's a box. All right. And I often say, because if you think about it, I don't know what the impedance of epic is, right? But I do know that epic probably has a P of a megawatt, right? And a power factor that's probably 0.9, okay, something like that. Okay, we don't typically know the impedance of those loads. So in this case, I'm going to start out with load 1 and load 2 in parallel. I know what VL is. I said VL is 208 with an angle of 30 degrees. Okay. Frequency is 60 hertz, and I know what all these other things are. Now, what I've been told here is actually three things, I guess, about load 1 and load 2. So this is load 1 stuff. And this over here is load 2. All right, I'm told that load 1 has got a 10 kVA. So S1, I should be careful, that's the magnitude of S1. Okay. 10 kVA. What do I call that magnitude? Parent power. Okay. And a power factor of 0.9, and I'm told that the load is inductive. All right. Same thing for the other load. I'm told that it's inductive. Okay. How do I use the fact that I'm told that the load is inductive? What does that tell me?
Do you know?
What's going to be between 0 and 90 degrees? The impedance angle is going to be between 0 and 90 degrees. Okay. So the fact that they're inductive tells me that for both of the loads, all right, for both of the loads, for Z1 and Z2, phi Z1 is between 0 and 90 degrees. Okay. And phi Z2 is between 0 and 90 degrees. And sometimes you'd say it's a leading or lagging. All right. So this could also be stated, again, I don't typically tend to state it that way, but this could also be said that this is a lagging power factor. And this could be this also. Why? Why do we use the term lagging if it's inductive? The current lags the voltage. All right. If I think about it, if my impedance angle is positive, the angle of the current is the angle of the voltage minus the angle of the impedance. It's going to be behind the voltage. Okay. Don't get too lost in that. You can think of it carefully by thinking about Ohm's law. Okay. All right. So here's what I want to do. I want to go through this power triangle for load 1 and the power triangle for load 2. So what that means is I want to calculate P1 plus J Q1. And I want to figure out for load 2, P2 plus J Q2. Okay. And then I want to figure out the phasor diagram. What's that mean when I say I want to figure out the phasor diagram? Well, I want to figure out where's the voltage, where's the current, all that stuff. Then I want to figure out what's the phasor IS and the phasor VS. What the heck am I talking about? The phasor IS and the phasor VS. Well, those are this current and that voltage. All right, those are the things I don't know. Okay. All right, so let's start. Complete the power triangle for load 1. All right, so what do we know? We know that the magnitude is 10 kVA. And we were told that the power factor is 0.9 inductive. So that told us that phi z was somewhere between 0 and 1. No, sorry, 0 and 90 degrees. Okay. All right, so I said start with the power triangle thing. Now the power triangle is basically where I have in the complex plane, I have a P, I have a Q, and I have, what's that? What's this thing here? That's, yeah, and its length is the magnitude of S, just to be clear. All right. And what's this angle? Phi z. Okay. All right, you guys help me out. So when I say I want the power triangle, I want to know what's the length of each side. All right, so I want to know what's P1 and Q1. So how do I do that? This is really just trigonometry. I don't even need to know anything about those formulas, really. If I know trigonometry, I could do this, right? Yeah, you're off. You're off, Musa. Yeah.
Power factor is equal to real power over apparent power.
Well, yeah. So what I would do is I would go back to those formulas and I'd be like, what the heck's he talking about, right? So basically here in my formulas here, real power is VRMS IRMS times cosine of this thing. And power factor, I should write down, is cosine of phi z. All right. So I look at this. VRMS IRMS is the apparent power. It's the length of S. Okay. Cosine of phi v minus phi I, that's the same as cosine of phi z. That is the power factor, right? So when I look at this, all right, I can figure out what P is because P is VRMS IRMS times the cosine of phi z. The cosine of phi z is the power factor. This is power factor 1, like that. Okay. So do I know VRMS IRMS? I know those as well, right? Because VRMS IRMS is what? The magnitude of S, right? I can go back to the sheet. That's the magnitude of S. Okay. So I've got that as well. So I know that this is 10,000 times 0.9 or 9 kW. Okay. I'll call that P1. Now, how do I figure out Q1? I figure that out.
The S1 times sine of the power factor.
Yep. Exactly. It would be S1 magnitude times the sine of phi Z1. Okay. So if I want to figure that out, what do I got to do? Well, I know S1. What do I not know?
Power factor.
Yeah, so I don't know the angle of the impedance. Sometimes we call it the power factor angle, right? So I don't know the angle of the impedance. So what do I got to do? Well, I got to figure that out. I got to say cosine inverse of the power factor is equal to phi Z1. Again, this is all just trig. This thing's just a triangle, right? And honestly, I don't even really need to go back to any formulas. If I know that the length, the hypotenuse, is the magnitude of S1, and this side here is P1, and this side here is Q1, I can go back to trig and forget that this is an electrical engineering problem, right? It's just a triangle. Okay. So I can figure out what, because this is, if you think about it, it's saying the sine is equal to the opposite over the hypotenuse, right? So if I go through this whole thing and I try to compute what that angle is and everything, let's see. So I did that. It's this angle works out to be, so phi Z1 works out to be 25.8419 degrees. Okay. And Q1 works out to be 4.3589. What are the units? It's K something. K var, yeah. All right, voltams reactive. Okay. All right. So we'll keep going. For the next one, for load 2, I was told that P2 was equal to 12 kilowatts, 12 kW. And I was told that the power factor is 0.85. Okay. I was also told that it was inductive. So what's that mean to be told that it's inductive? What's that tell me about the angle? It's positive. Yeah, it's between 0 and 90. Okay. All right, so this is by Z2. All right, so in terms of that triangle, notice all these problems, you're going to be given two things about the load. You're going to be given what its angle is somehow. So the power factors kind of told me the angle. And then I'm told one of the length of one of the sides. And from there, I can figure out everything else. Okay. So which side of the triangle am I given here? Yeah, the real axis part. Yeah, I'm told that this is 12. P2 is 12 kW. All right, so what do I got to do? I got to figure out here my Q. I drew Q going up, not going down. Why is that? Because the angle here of this vector is going to be between 0 and 90. Okay. And then this guy has a length here, S2, like that. And I'm going to keep referencing that with the bars to say that it's the magnitude of it. The whole thing is a vector, right? So I'm going to refer to it with the bars to say I'm dealing with a magnitude. All right. And this angle here would be phi Z2. Okay. All right. First of all, would be, how do I figure out phi Z2? How do I figure out that angle? How can I figure that out?
The arc cosine of the power factor angle.
Yep. So I do, well, arc cosine of the power factor, right? And that works out to be, if I do the math, 31.7883 degrees. Okay. Now, what else do I need to know about this here thing? Yeah, the magnitude of S, right? So how do I get the magnitude of S?
Isn't that just power divided by?
Yeah, so if I know the power factor, the magnitude P2 is that, right? P2 is the magnitude of S times cosine phi Z2, right? Or the power factor. So in other words, I have magnitude of S2 times the power factor, which is 0.85, is equal to 12 kW. Right? So this is going to work out. So 12 divided by the power factor works out to be 14.118 kVA. Like that. Okay. Now I got a couple of ways that I could figure out the Q here, right? How can I figure out the Q?
Root over magnitude squared minus P2 squared.
Well, so yeah, so I have that the magnitude S2 squared equals, so magnitude is equal to the square root of P squared plus Q squared, right? So I could solve for it from there. That's one way to do it. The other way to do it would be to say that Q is equal to the magnitude of S times what? Times the sine, right? So again, there's formulas for it all. They're ugly, there's many, but it's just trig, right? Where'd you get this? This is the Pythagorean theorem, right? It's not too tricky. All right, so my Q2, if I go through that, my Q2 through either of those two approaches works out to be 7.4369. And what units do I give that? kVARs, volts amps reactive. Okay, volts amps reactive. Okay. All right. So I did the first two parts of that. The next part is I wanted to figure out the phasor diagrams for both the loads. When I say the phasor diagrams, that means I wanted to figure out what's the voltage and current relationship look like. Okay, so I was told, if I go back to the picture, is that clock right?
It's like 5:03.
Okay, yeah, all right, so it's about right. All right, where'd it go? Oh, yeah, I went too far. I was told, this was my setup, right? So I was told that the voltage across the load is 208 with an angle of 30 degrees. Okay, 208 with an angle of 30 degrees. So my phasor diagram, I'm going to show here is the voltage, and here's 30 degrees. So what I'm really asking for when I draw that phasor diagram is I want to figure out, okay, well, where's the current going to be? All right, where's the current going to be? Now, because this load's inductive, without doing any math, where is the current going to be? I don't want an exact number, but where is it going to be relative to the voltage? It's going to be, well, it may be in the fourth. It's going to be lagging it, which means it could still be in the first quadrant. In other words, it's going to be somewhere that direction where the current's going to be. Could still be in the first quadrant, possibly, depending on what the angle of Z is, right? But it's definitely going to be lagging it, right? So it better be maybe in the fourth quadrant, maybe in the first. Okay. All right, we can figure that out. How? How can I figure that out?
Phase of D is equal to the phase of D minus phase of I.
Yeah, so knowing that I know the impedance angle right now, I could get to the angle pretty quickly. All right, there's a couple of ways I could do this, right? So I have that the magnitude of S is equal to VRMS times IRMS. So that'll give me, I guess I should call that IRMS1. Okay. And I know that from Ohm's law, V equals, I called this VL. VL is equal to I1 times Z1, right? So in other words, I know that the angle of V equals the angle of I1 plus the angle of Z1, like that, right? So I know this already, and I know this already, so I could figure out this. This will tell me the magnitude. This will tell me the angle. Okay. Now, that's one way to do it. There's a couple of other ways to do it, right? What I actually did, I think, right, was I actually did it a little bit differently. What I did was I said S1 equals S1 as a vector equals VL as a vector times I1, the current in this thing, as a vector. All right, so if I had to, just to be clear, here's the load. So there's a VL across it. There's an I1 into it. Like that. Something's wrong with this. It's conjugate. Okay, it's conjugate. Right. So what I actually did was I did it like this, right? And I know the S1 vector, because what is it? It's P1 plus JQ1. Because we just solved for those, right? We solved for P1 and Q1. So what I did was I actually put them in as a vector, right? And I took that vector and divided it by the voltage vector and got another vector. That's another way to do it. Okay. Both of those methods will work. Okay. If I do the math, either way, what I'm going to end up with is that the magnitude of I1, which is that IRMS1, it's written there, that'll work out to be 48.0769 amps. And the angle of it, so what I called phi I1 here, I guess, is equal to, so it works out to be in the first quadrant, 4.1581 degrees. It's lagging, right? But it's going to be right over here. Like that. Okay. So here's I. Like that. Okay. Now I do the same thing for the other load. Exact same approach for the other load. All right. When I do the exact same thing for the other load, I end up with I2 as a magnitude of 67.8733 amps with an angle of, in this case, it is in the fourth quadrant, 1.7883 degrees. All right, barely over into the fourth quadrant. Okay. Again, same approach to get that. Okay. Now, the other question I asked here is how do I get the current phasor IS? All right. So just to be clear, this was I1 going into here. And this is I2 going into here. So how can I get IS? KCL. Okay. There's other ways to do it, but to get IS, do KCL. I1 plus I2, like that. Okay. How do I get VS in this circuit? How do I get VS? Yep, KVL, right? I said I only know three things. We just did all three of them now, right? This is the third one, KVL. So basically I have that VS is equal to VL plus, now what's, oops, I'm putting this on the wrong slide. VS equals VL, voltage across the load, plus the voltage across RS and LS. So how do I write that? How do I write the voltage across RS and LS?
IS times Z.
IS times Z. Yeah, so IS. So what's the Z of those two things in series? RS plus J omega LS. Why does everybody want to make it W? It's omega.
Not basic like that. So I say,
I'm bougie, I guess. I don't know. It's omega. Right. All right. So it's RS plus J omega LS. Right. So that then gives me the phasor for whatever that voltage source is that I've got there. Okay. So I had one other step here. Right. Add a capacitor in parallel with the loads to make the power factor unity. All right. What the heck am I doing? So what am I trying to do? I know that this thing right now, these two loads in parallel, they must be inductive because if I look at it, they're both inductive, right? So they're combined, they're not going to become capacitive when I add them together, right? If I put a capacitor in parallel with those things, right, like that. In other words, I slap a capacitor in parallel with the two loads. What's the total power going into those loads? The total complex power into those loads, if I have capacitor and then I have load 1 and load 2 like that. Right. What is S total? That's the total power going into total complex power going into all of them. How can I write that? If I have 3 loads in parallel, how do I deal with their powers? They add, right? So I can say I've got S1, that's the power from load 1, plus S2, that's the power for load 2, plus what? Plus the power of the capacitor, okay? That's for this guy. Now, if I want the power factor of the combined thing to be unity, all right, what's that mean? I want the angle of S total to be 0, okay? So that means I want this guy to basically have a P total like that. That's it. So the only way for that to happen would be if what has to be true, I guess, about the what's SC look like, by the way? If I were to SC as a vector, what would that look like if I have a pure capacitor? It would be negative J QC, right? Why negative J?
So it'll cancel out.
Well, it has, so when we had an inductive load, the angle was always going to be what? Positive. If I have a capacitive load, the angle is always going to be negative. So I get a negative Q, all right? So what I'm doing is I'm basically trying to source some energy to balance the energy for the inductor, right? That's basically what we're trying to do. So, all right, so first thing I would do is I'd have to figure out, well, how much QC do I need to add in there? All right, how would I figure that out? How would I figure out what QC needs to be to make that happen? Add S1 and S2 together, right? So if I add S1 and S2 together, right? If I add those two guys together, I find that the combined version of these guys is 21 kilowatts plus 11.796 kVAR with a J on it. All right, like that. Okay, I need one more minute. Now, to relate that to a capacitor value, what I do is I go back, so I have a formula that I never bother kind of deriving, but basically here, right, the reactive power, all 3 of these reactive power things are equal to each other, right? So basically what I have is the VRMS squared divided by the imaginary part of the impedance is equal to Q, right? So basically what that tells me is this, that QC is equal to the voltage magnitude squared divided by the magnitude of Z sub C, like that. Or it doesn't even need to be the magnitude. So actually the signs will cancel out. Okay. So if I do this, I work out that Z sub C is equal to 3.6677 ohms. Okay. So how do I relate that to an actual capacitor value? How do I relate that to a capacitor value? What do I know about Z sub C? Particularly its magnitude. Yep, 1 over omega C. And I told you omega, the frequency was 60 hertz. So I know what omega is, you can figure out C. So I ultimately get to C is equal to 723.22 microfarads. Okay. All right. What I also have here, and I'll publish these as the after version of the notes. Okay. And I'll also publish the recorded lecture here. One thing I also did for each of those parts here in the notes, for those that want to see how I did it, all right, is how I calculated and put it into MATLAB. All right. I just make MATLAB do all the work for me. All right. And again, you don't have to, you can. All right. And so I put in basically how I calculated each one of those parts there. Okay.
That would be plus also, right?
Yeah, that's supposed, yeah, so that's already posted actually in so in my before, like I just have a bunch of blank slides here, like I
I
just,
just want to make that extra.
Yeah.
And that's fine.
Yep. Right.
Yeah. Good.